Let's go through a couple. Here's kind of the plan for today. I've got tomorrow. We're going to talk about second derivative test, but I didn't want to throw that on you today. We needed, I think, haven't been together very much. So I want to take a day and go back and kind of catch back up to speed on the first derivative test, and there's a couple mean value theorem problems I want to maybe look at just to review that too real briefly from 3.2. But then we'll move on to 3.4, which is the second derivative test. Okay. If you're wanting to, I know there's still some people who are probably still needing to do related race tests. Any day's fine. I'll be here after school today and Wednesday. Any day during TA is fine. I mean, we can find times, but today I can be here. How many people have spring sport commitments? Raise your hand. How many people are able to get here after school occasionally?
Next week.
Next week? Oh, yeah, next week. Okay, but some of you guys, okay. So after school is a good one, and then the rest of you guys, I'll just remind me to be getting here for TA when you want to. Okay, so let's look at finding where the function is increasing, decreasing, and all relative extreme. And the thing, once again, I want to really hammer home here is this is table stuff, right? This is where we're going to build our big derivative tables, and everything we're going to do for the next, week and a half. All of that stuff gets explained and represented well in the table form, right? So we're going to end up with we got our X row and our F row and our F prime row, and then starting tomorrow we'll add an F double prime row, which really actually makes things a ton easier. It sounds like more stuff, but it's good stuff. It actually makes a lot of these problems a lot easier. Okay, so in order to get going on that, though, what do we need to do with our function? Okay, so where the function's undefined. Good. We want the domain of the function. Very good. So what is the domain of this function? Are there any values of x where this is undefined? Zero. Okay, good. So the very first thing we want to do is we want to tack on here x cannot equal 0. That's our domain, right? And when we make our table then, I'm going to go give us a little room to work here. When we make our table, how are we going to represent that domain in our table, do you suppose? I mean, that's a pretty important number, 0.
We put 0, we go down to f of x until undefined.
Okay, so on the F row, that's going to be undefined. Okay. There are no endpoints. So how do you suppose I could indicate that on row 1 for x?
Negative infinity, positive.
Open interval from negative infinity to positive infinity, right? So I put rounded brackets, negative infinity, rounded brackets, positive infinity. So we got the entire real line to work with for our domain except for 0, okay? And then we're going to need to have some information about f prime. So what do you suppose we do next? Take the derivative, okay? So we got a couple choices here. Let's talk about this derivative. We want to be like all things calculus. It really pays to pause for a second and think about this to pick the best route. What are our options for differentiating this function? Well, we could, but we don't really need to do that. We can make it easier than logarithmic. So as it's written right now, what rule would we have to use? Quotient rule, right? Because we got a quotient of two functions, right?
Yeah.
But could we rewrite this in a quotient rule? To me, I mean, that's not like the worst thing in the world, but it's pretty bad. I mean, it's not our favorite thing to do, the quotient rule. Can we avoid it?
Yes.
Okay, how could we rewrite our function here?
X to the 4th plus 4 times 1 over x squared.
Okay, so we get common denominator. What's x to the 4th over x squared?
X to the 4th plus 4 times 1 over x squared.
Okay, but we could even do better than that. What if I split this into separate terms? I get x to the 4th.
Over x squared plus 4 over x squared.
Okay, so what's that look like? What's x to the 4th over x squared? We can simplify that. X squared. Okay, plus 4x to what power?
-2.
There you go. So isn't that better? Right, that's easier to deal with. Now we can just differentiate term by term using the power rule. Much easier, right? So what do we get? Derivative of x squared? 2x. Derivative of 4x to the negative 2,
Negative 3, yeah. That's the negative 3.
negative 3. Good, right? We got to remember, we got to subtract them. So if we want to write that, there's a couple ways we could write that. One thing we could do, we could write it as 2x minus 8 over x cubed. That's fine. If we want to, we could even write this thing, you know, and you could debate the merits of either one. I could get a common denominator and multiply by x cubed over x cubed if I wanted to, right? And that would give me 2x to the 4th minus 8 over x cubed. And that's the answer we would have gotten if we had done quotient rule, right? But this is really fine, isn't it? Okay. There's our derivative. Now we got to find all the critical numbers. So let's remind ourselves here, how do we use a derivative to find critical numbers? What are the two kinds of things we're looking for? Okay, where it's equal to 0 or undefined. Let's take the undefined first. Where are the places where the derivative is undefined?
0.
0, but
It's not a critical number because it's undefined.
yeah, it's not a critical number because that's already a place where the function doesn't exist, right? So that one's not a critical number because it's not in the domain, right? So there's no place in our domain where the function is undefined, okay? Let me make a note of that. F prime is nowhere undefined on our domain, right? Okay, where does it equal 0? Okay. So I need a little more room for that. I'm gonna. Oh, darn
At
Oh,
4th root of 2.
it. I'm gonna have to write small. Okay, so f prime equals 0 when this equals 0, right? Isn't that the same thing as saying if I set that equal to 0, I could just add that term to the other side? So I would get the equation 2x equals 8 over x cubed, right?
Yes.
Okay, so how could I solve that?
You multiply your side by x cubed.
Okay, good, cross multiply, right?
Divided by 4.
So, and I could divide each side by 2, and I'm gonna end up with x to the 4th equals 4.
No, x to the 4th equals 2. Wait, no, right. Yeah.
Equals 4, okay?
And then you take the 4th root of 4.
Okay, but let's take that in steps. We can take a 4th root, but taking a 4th root that's just not a normal thing for us to do. There's an easier way to do this. So let's go to there. So x to the 4th equals 4. We could take a 4th root of both sides. We have to do a plus or minus if we do that. But what else could we do? We could do this in a couple steps.
Both sides.
What could I do?
Square root.
Square, everybody agree? We can square root both sides? So if I square root, right, if I square root both sides, then that's gonna give me x squared, which is taking it to a 1/2 power, equals, because I square rooted both sides, you know, think back to algebra 2, how many times did we harp on this, or probably in pre-calculus too, if you take the square root of both sides of an equation, you have to introduce a plus or minus, right?
Yes.
So we get plus or minus, and then the square root of 4 is 2. Right, so now we've got at this point, we've got two solutions. We've either got x squared equals 2, or x squared equals negative 2. We're looking for open intervals on which the function is increasing. So are we going to get an extrema? You know, I want critical numbers. Are we going to get any real critical numbers from this?
No.
No, we're going to get imaginary, right? Okay, so this one we can bail on. No critical numbers coming from that equation, but this one we do. If I square root both sides, what do I get? Square root of 2. Plus or minus square root of 2. Good, so those are our critical numbers, right? So the first derivative is equal to 0 when x equals square root of 2 or negative square root of 2. So we recognize those as critical numbers, right? Okay, make sense?
Yes.
So how are we going to check to see whether those critical numbers are extrema or not? No. I mean, I might end up doing that for my sketch, but that's,
We'll
so,
start plotting points in between.
okay, so we're gonna pick test points, right? But I'm gonna go back to what Tyler suggested first. Let's just talk about that for a second. If I plug these into the function, remember, I'm just getting ordered pairs, right? Those might be important to us, because ultimately, if we're trying to come up with a sketch of this graph, and that's where we're going with this, we're just really focusing on, in section 3.3, I'm hammering increasing and decreasing intervals and finding relative extrema using the table. I'm not really having you guys come up with sketches of the graph, but we're really focusing on that skill. Section 3.4 is going to be working in the next row, talking about concavity, which we haven't even defined yet, that's for tomorrow, and the second derivative test, and we're hammering that skill. But then we're going to come back, and I'm going to give you a couple, I think, really important assignments. These are sort of benchmark assignments, where we're going to take everything we've learned in Unit 3, and we're going to put it together, and we're going to pick the best method of all the stuff we've learned. So either first derivative test or second derivative test, and we'll talk about, when you pick which one. And fill out the table, and then you're going to develop a sketch of the graph based on the table. Okay? Right now, we're not really emphasizing that, but that's where we're going with this. So in the back of your mind, be thinking in that way, right? So it might be useful for us to be able to come up with an ordered pair, because that tells us where those key points are on the XY plane, right? Okay, but if we want to know what these critical numbers are, the first derivative test, that's the one where we're going to pick the easiest ones we can. We're going to pick some test values to the left and the right of each of these and look to see what the sign of the first derivative is there, right? Because what are the only places where the first derivative could have a value of 0? Therefore, change that critical number, right? And that critical number. There's no other places where the sign of the first derivative could change. Now, something weird's going on here, but we'll talk about that in a second. We'll get back to that. So what are some good tests? Let's pick easy ones. What are some good test points to pick around negative radical 2? So that's about negative 1.4142, blah, blah, blah. Okay, so negative 2, negative 1 would be convenient ones, and positive 1, positive 2, right? And then all we've got to do to fill in these blanks there, and there, and there, and there, is evaluate the sign of the first derivative. We don't care about the value at all. We just want to know, is it positive or negative, right? So let's go to that's where this is a little bit more convenient, isn't it? I mean, either one of these will work. The thing is, we already have this solved in terms of, being as we did the work there. Let's take this representation of the derivative, and let's check the signs of each of those critical numbers. We'll go to the next page because I'm running out of room. Okay, and then we just had, our critical numbers are just negative 2, negative 1, 1, 2, right? So f prime of negative 2. So if I plug in negative 2, on the top, am I getting a positive or a negative? Positive, right? I'm going to get a, what is that? 32 minus 8, so I'm getting positive divided by negative 2, that's negative, so the overall sign is negative. So we'll go back over here, and we can do negative there, right? What if we evaluate the first derivative at negative 1? On the top I get negative. On the bottom I get overall sign positive. Right? Okay, what about at 1? So let's just go over here. F prime of 1 is going to give us negative over, so negative. And while we're at it, let's do this one. F prime of 2. Positive over positive. Okay, so negative, positive. Okay, so that tells us what is going on here. Remember how we do this. If it's a zero first derivative, what's that tell you about the shape of the extremum? Smooth or jagged? Smooth. So we can have a tangent line, and then we're going, I hear you guys saying we're going from decreasing to increasing. So it's got to be a minimum, right? Over here, once again, we've got a horizontal tangent. We're going from decreasing to increasing again. So that's also a minimum. Did I do that right?
Yes. Yes.
Negative, there we go. Okay, good. Okay, so far so good. Now, what's going on here?
It's an asymptote.
Okay, it's a candidate for an asymptote, right? We got to check. So what is, now if I try to evaluate the function at 0, what am I going to get? So where am I going to put this? Okay, this is going to be up here. So if I try to evaluate my function at 0, what's the result?
4 over 0.
4 over 0. Now we got to think clear back to the beginning of the year. It's been a long time ago. But when we evaluate a function, if we have a solution, a 0 of the bottom but not the top, that always is what? Asymptote, right? Now what if it were a shared 0, top and bottom? Oh, that'd be a hole, right? This is clearly, because of this, this is a vertical asymptote, okay? So when you have a vertical asymptote on a function, here's how you almost have to think about that. It's like dividing this whole xy plane into two separate universes. They're completely separate, right? We have to deal with them independently. So if we did want to come up with a sketch of this thing, well, let's go ahead and add our ordered pairs here. So if I evaluate my original function at negative radical 2, what are we going to get? So let's go down here.
3 over 2.
So f of, so f of negative, what was it? What was our asymptote at? Oh, no, our critical numbers was negative radical 2 and positive radical 2, right? So f of negative radical 2 is going to be, is that 4 plus 4? Is that right? Squared, negative square root of 2 squared is 2. Squared again to get to the 4th power is 4, right? So we're going to get 4 plus 4 over 2 equals 8 over 2 is what, 4? So we got the ordered pair negative radical 2, positive 4. And then we're going to get the same thing here, aren't we? Right? Okay. So now let's take this table and let's come up with a sketch for this thing. Even though we're not really doing that so much in this section, we're kind of thinking ahead a little bit, right? So we got there we go. So what's this look like? If we want to come up with a quick sketch, and this might seem weird, and you might be asking yourself, why would we bother coming up with a sketch? Well, because we don't really graph things in calculus very much. We just sketch them. We don't really care exactly what the function looks like, but we want to know what is the overall shape, and we do specifically want to know what are the points of interest to us. Well, the 2 points of interest are there and there, right? So those we're going to anchor. We'll know precisely where those are, but the rest of this stuff is just going to give us an idea of what the basic overall structure of this thing is, right? Okay, so we've got, there's the XY plane. Well, we know we've got a vertical asymptote there, right? if we go back to this point at negative radical 2, positive 4, so that's about right there. Over radical 2 up 4 is right about there. Okay? And we know that the function, this is a minimum and that's a minimum. And so what's the shape of this thing have to be? Doesn't it have to do something like it's going to go asymptotically up the axis there, right? Now, if we go back and look at the original function, if we were to take the limit of our function as x approaches infinity, wouldn't you agree that we're going to get infinity on the top, right? So it makes sense. If we look at the end behavior of the function, it also makes sense with our picture, because our picture is just going to do that, right? Okay? That's not exact, but it's pretty close. The main thing is we got the coordinates of those points. Okay, what do you notice about, we got this picture now, what do you notice? Is there something else going on here? Can you see some symmetry? What do you notice?
Y-axis.
Okay, so it's got folding symmetry or line symmetry over the y-axis, right? So now let's go back and let's think about this. You know, we hit this in Algebra 2 a little bit, but this would have been more of a last year thing probably, right? Let's quickly review something else that's a good tool for us. What's the definition of even symmetry, right? If we want to have folding symmetry about the y-axis, I think we touched on this once this year. See if you remember.
If one of the requirements points,
Yeah.
you can reflect it over the y-axis.
Okay, that's the result. So if we've got
Function.
even symmetry, that's symmetry about y-axis, right? If we've got odd symmetry, that's rotational symmetry about the origin, right? Right? What's our test for this? F of negative x equals what? F of x. So in other words, what that means, if we want to describe that using words, we would say that F is insensitive to negative x. If I make x negative, it has no impact on the overall graph, right? Odd symmetry is what?
F of negative x equals negative f of x.
Okay, so if I evaluate the function at negative x, it gives me negative y also, right? Okay, which makes sense, doesn't it? I mean, that's going to give us, think about it, if I go over x and up y, and I want to rotate this thing about the origin, then I'm going to go back x and down y, right? Makes total sense. Well, what about our function? Where do I have that thing written down? It's real clear back here. What about this guy? If I evaluate this at negative x, what do you notice? The negative disappears everywhere, doesn't it? Because I've got an even power of x and an even power of x, right? And so I can tell by my test that f of negative x equals f of x. So how could we have taken a great big shortcut here from the beginning if we had kind of looked ahead? Just do half, right? We could have just done this half of the function and then reflected our results, right? See that? Symmetry is huge. You really want to take advantage of symmetry whenever you can. And that saves a lot of work, a lot of work, okay? Okay? Okay, let's look at, when are we out of here? 18, okay, so maybe we'll just look at one more example here. That's probably good for today. Let's look at an actual application of this stuff, right? Say it again. It kind of, at first glance, it sure looks like that's going to be a logarithmic one, doesn't it? Because we got lots of products going on there and quotients. But it gets a little bit easier. The electric power in watts in a direct current circuit with two resistors, R1 and R2, connected in series. This is how we calculate power, right? If we're looking at like circuit design stuff, physics stuff, okay? Where V is the voltage, and the resistances are R1 and R2, and P is power. So if V and R1 are held constant, that's big, right? What's that telling us? what resistance R2 produces maximum power? Only one variable, right? There's only one variable, and that variable is R2, right? So really what we've got here is P of R2 equals all that stuff, right? But it makes it a lot simpler because I don't have to worry about, this looked like it was going to be horrible, like we're going to get product rules in the numerator and quotient rule and all that stuff, but no, we just have a constant times, R2 divided by R1 plus R2 squared, right? So we could go ahead and use quotient rule on this, right, and differentiate. And what do we get if we differentiate this guy? So we're going to get P prime. And I'm actually going to write it down as dP dr2, right? Because we're differentiating with respect to R2. All the other stuff is constant. Equals. Well, that's a constant. I can just pull that out front, right? Just leave that out front if I want to. And then I'll just do that quotient, right? So this is really the only stuff I need to do in the quotient rule. Take your pick. I could just think of the top, I could leave that attached to the top if you want to. We usually do it that way. Let's do it once this way just to kind of remind ourselves that this is another option. Pull the constant out front and just differentiate the blue quotient, right? So what's that going to give us then? Quotient rule, what's that again? Low-D high, high-D low. So we got low R1 plus R2 squared times the derivative of high. What's D high? Derivative of R2 with respect to R2 is 1, right? Minus high times D low. Yes, sir. Inside of, when you say that, what do you? Well, yeah, we're going to, but we haven't done that yet, right? We did low times D high. D high is easy. D high is just 1 minus high. Now D low's chain rule.
Oh, yeah.
Now we're differentiating the bottom. So the derivative of the bottom, we're going to have 2 layers. I've got the derivative of hand squared is 2 hand, right? So the first step is going to be times 2 hand to the 1 times the derivative of hand is 1, right? I get the derivative of R1 is 0 because that's a constant. The derivative of R2 is 1. Okay? Oops. Need a new color. Okay, divided by no, the denominator squared. So hand squared squared is just hand to the 4th, right? So on the bottom we get okay. Now let's pause there for a second. Take a second and everybody look at that, and I want to see hands. If you're not sure about something, stop us right now, because we got time. We got 9 minutes and we don't have that much stuff. So. Does that make sense, that derivative?
Let's
We will. Okay. Yeah, it kind of does, I agree. Kind of does. Okay? Okay with that? Good. So now, what can we do? Well, let's work inside the brackets here. We got to simplify this. What are our options again? I know this gets boring talking about the options, but man, say it again. Everybody see that? Okay, that's a good idea. The alternative would be, and you might be thinking this, is square this out, distribute the 2R2, right? But that's going to give me something kind of messy, isn't it? I'm going to get a big quadratic expression. Why not always factor out a common factor if we can? So we'll pull out an R1 plus R2. So we've already got this constant out front, VR1. We're going to undistribute an R1 plus R2. And what's left behind when we do that on the top?
One.
I took one of those away, so I got one of them left,
R2
right?
minus
So,
R2.
okay, so I get an R1 plus R2 minus, and I'm gonna put a green circle around that so we can see that that's the same minus sign separating the terms. Then on the other side, all we're left with is just what, 2R2? Okay. And then that whole thing is divided by the denominator R1 plus R2 to the fourth. Okay, this is gonna simplify, isn't it? R1 plus R2 minus 2R2 is what? What's that all simplify to?
R1 minus R2.
R1 minus R2, yeah.
And then you take an R1 plus R2 and right out the bottom, right?
Yeah. And we could cancel one of these, right? Then I've got this factor there is gonna cancel with one of those, right? And so we end up with our derivative. This looks pretty messy. Well, so I've got a V R1 times R1 minus R2 divided by the quantity R1 plus R2 cubed. So there's our derivative. That's a lot of work, but we're there. We got our derivative. Okay, now we just have to make our table, right? We need critical numbers. Okay, so where are the critical numbers here? Where is,
When R2 equals negative R1.
let me take a picture of this, I need more room. To be continued, next page. Okay, so P prime is, or equals 0, let's say. And what's true? If I have a fraction, where's the fraction equal to 0? Where the top is 0. So would you agree that P prime is going to equal 0 when R2 equals R1? Right? Okay, from here. Right? Okay, now what about this one? You gotta be real careful with this. Whoops. P prime is undefined when what?
Equals negative R1.
Okay, when the bottom equals 0, right? Remember, R1's a constant, so R2 would have to equal negative R1, right? Okay, now let's think about that.
Produce negative resistance.
Yeah, let's think about that, right? So mathematically, that's a critical number, but this is not a strictly mathematical situation, right? This is a mathematical model of a physical situation. So if we go back to our very first page here, if we had looked at our domain again, what's the domain of this function? Well, mathematically, we might say R2 cannot equal negative R1 because that gives us 0 on the bottom, right? But we're talking about electrical resistance. Now, you guys talked about resistance in physics. You guys have done some circuit stuff.
We talked about it.
You just talked about it a little bit. So what do you know about resistance? Can it be negative?
No.
No. Smallest value resistance could ever be would be in a superconductor where it's equal to 0, right? That's the lowest you could possibly go is 0 resistance, right? So we know because this is a physical situation, R2 has to be greater than or equal to 0, right? That's our domain. And so we move up to this page up here. This really not in domain. That can't work. Right? And so we could make a table out of this thing. So we've got R2 is our independent variable instead of X. We had power is our dependent variable, and then P prime. Okay, so what's our domain? 0 to infinity, right? infinite resistance, what would that mean, physics types? Yeah, it's a perfect insulator, right? So that'd be like styrofoam or something, right, would approach that, okay. High resistance. The one critical number we got was at R2 equals R1, which is, who knows? I mean, we don't know the value of R1, but whatever it is, whatever R1 is, that's our critical number. That's where P prime equals 0, so that's a critical number. And then if we just pick some test points, like what would our test points be here?
Sounds like
What's a test point on our domain there? 0. 0's included, right? So that's a good test point. What's a test point bigger than R1?
infinity.
Well, we don't want to, that's tough though. We don't really want to use infinity because that's hard to evaluate. We have to take a limit. But if, I mean, what's an easy one? We don't know what R1 is, but how about like 2R1 or something, right? Whatever R1 is, we could pick another test point out here at 2 times R1, right? And see what we get for our sign there. So now if we go back and evaluate our derivative, which is right here, okay? If we pick 0, so what is, oops, back here. Let's do P prime of 0. Remember, R2 is what we're plugging in. What's that going to give us? If I put 0 in for R2, what's the sign of the top going to be? Positive. Because R1 is positive, it has to be, right? And on the bottom, we get
Positive.
positive. Okay? So we get positive there. I guess it's here, whoops. It's there. And then at 2R1, what are we going to get? P prime of 2R1. On the top, we're going to get what? Negative. Yep. On the bottom, positive. Right, bottoms, we're adding 2 terms that are both positive, right? So overall sign is negative. So, hey, we just made it. So what's that give us here? We got a horizontal tangent, and we're going from increasing to decreasing.
It's a maximum.
Everybody agree? So we got our max for power then, right? That's pretty cool. We can do that.
Sierra, Quail, Allie, and Zach, Brad, please come to the office. That's Sierra, Quail, Allie,
So you're trying to complete
and
square.
Zach, Brad to
Okay.
the office. Thank you.
You'd have to just multiply both sides by -1. Which
That's
makes
what
that
you did.
positive, and that's negative.
Well, so I already did that.
Lily, I'll tell you, I'll tell you if I need an application or not.
Oh, okay, yeah. My mom said that she could
So,
get one
yeah,
too.
it's negative.
I'll find out and tell you.
Yep, it could be
Can we put
negative
the
up
answer
front.
Yeah.
You wouldn't write it as one, just a negative, the quantity x plus 1 squared plus 1. Yeah, you got it.
Hi.
Hey, what's
I
up?
was wondering if I could see my score on the related grades test.
Yeah, did you never see it? You were gone when we went
No.
through that, didn't you? No, you did really well. You can.